Hello everyone. We're solving dynamics problems. Our topic, rectilinear motion. A ball is thrown vertically upward from point A in the figure with an initial velocity of 40 meters per second. Find the distance h from the point where the ball returns to point B and the time t from position A to position B. Also calculate the velocity Vb at which the ball hits point B, neglect air resistance and the small horizontal movement of the ball. So, what values will we find now? The distance h between the point where it returns and position B. The time t, from A to B. And the velocity Vb at which it hits B. We've been asked to find these three quantities. What kind of motion is this? Rectilinear motion, but with constant acceleration. We'll examine rectilinear motion with constant acceleration. Vertical motion. A vertical projectile upward. It is thrown upward from point A with a velocity v0. After a certain point, it returns and hits point B. When solving dynamics problems, we consider a specific interval, the beginning of the portion of the motion under consideration and any subsequent instant. Two positions. We solve by considering two instants. The values at position 1 can be called t1, s1, v1, a1. The values at position 2 can be called t2, s2, v2, a2. Generally, the quantities at position 2 are taken as general quantities, such as t, v, and a. They are taken as any instant. But the values at position 2 can also be specific. Now, let's consider position A as position 1, and the return position as position 2. Let's call the return position position C. Let's assume t equals 0 at position A. If possible, we try to set t to 0 at the beginning of the interval we're considering. We set t to 0. There's no reason not to set t to 0 here either. We set t to 0. At A, t is 0. We don't know the t at C either. We could also call it any t, tc. Let's move on. Let's move on to the position. We need to make another choice for the position. We'll choose an origin. We'll choose the position where s is 0. And we'll choose the positive side. This choice is arbitrary. Anyone can choose as they wish. But of course, the choice made can make things easier or more difficult. You need to make your choice carefully. I'm choosing the origin as the beginning of the motion. I'm choosing position A where s equals 0. I'm choosing the positive side as the upward side. In this case, v0 will be positive. The acceleration will be negative. Since it's downward, the acceleration is negative. I've chosen s to be 0 at position A. The position at position C is s equals 50 meter plus h, at position C. It's above B by a height h. Let's move on to the velocities. The velocity at position A is given. Its vertically and upwards is 40 meters per second, v0 equals 40 meters per second. What is the velocity at position C? The velocity at position C is 0. It returns to the position where s is maximum. It doesn't go any further. It goes up and up. Finally, it returns from that point. This means s is maximum. S, the scalar position, has reached its maximum value. We know that the derivative of the scalar position with respect to time gives the velocity. A function has a maximum or minimum where its derivative is 0. The extremum of a function is where its derivative is 0. The slope of its tangent is 0. Therefore, if the scalar position, s, is maximum at point C, then the velocity is 0 there. Let's move on to the acceleration. We know that the acceleration is vertical and downward. Its value is 9.81 meters per square second. Since we chose the positive side up, depending on the direction we chose, at every instant, at every location, everywhere a equals minus g, and it is equal to a0. It is equal to the acceleration at the initial location. a0 is also equal to minus g. It is also equal to minus g in a2, ac, and ab, everywhere a, is equal to minus g. This motion is a motion that changes direction. It changed direction at point C when going from A to B. We see that it slows down from A to C, because the acceleration vector and the velocity vector are in opposite directions. After C, there is also an acceleration from C to B. Because the acceleration vector and the velocity vector are in the same direction, it turns downward. After C, it accelerates. The velocity also turns negative. The velocity also becomes negative. The acceleration was already negative. Thus, acceleration occurs. So, what is it? Even if there is negative acceleration, acceleration can occur. Negative acceleration can also accelerate. Let's move on. Now we want to find the distance h. We can find the distance h using the relations we obtained earlier. From the timeless velocity formula, let's find the distance h. The only unknown here is h. We know the other quantities. We know the required quantities at position A and position C. The final velocity is the velocity at position C, that is, v, which is also 0. We know the initial velocity. We know a0. We know s0. We also know s, 50 meter plus h. Substituting these values into the equation, we find h equals 31.5 meter. Now let's find t. Let's choose A as the first position and B as the second, and find t. Let's find the elapsed time. We chose t as 0 at position A, s0 is also 0. A is always the same. It is equal to minus g. We call t at position B the time at position B, t. We will find that s at position B is 50 meter. The acceleration is again minus g. Let's look at the velocities. The velocity at position A is the initial velocity. The velocity at position B is the velocity of impacting the ground. The velocity of impacting point B, we don't know that either. Now let's find t. We can find t using the s function t relation. In this relation, the only unknown is t. If we substitute the known values, we can find t, s is 50 meter. Final position is position B. The value of s at point B is 50 meter. S0 is 0, V0 is 40, A0 is minus g. If we substitute, we obtain a quadratic equation. This equation has two roots. The first root is 1.5 second. The second root is 6.6 second. So, what is the answer to this question? Which of these roots we found is the answer? Both could be the answer. In other words, both roots of a quadratic equation could be the answer. Either one could be the answer. Which answer are we looking for? The first root is 1.5 second. This is the instant when the particle passes upwards from the level of B. That's not the answer we're looking for. The second root is 6.6 second. By the time it returns to B, 6.6 second will have passed. That's the answer we're looking for. T equals 6.6 second. 1.5 second isn't the answer. That's not the answer we're looking for. Yes. Now, let's find the velocity upon impact at point B using the equation v equals v0 plus a0t. The only unknown here is v. It's the final velocity. We know the initial velocity. We know the acceleration. And we know the time, t, that elapsed to point B. So, we can substitute the known values and find vb. We can find vb using the equation vb equals v0 minus gt. We find vb equals minus 24.8 meters per second. What does the minus here mean? It indicates direction. It indicates that the velocity is downward, that is, negative. We already know this should be the case. The magnitude is also 24.8 meters per second. Now, let's find the velocity v another way. A second alternative. An alternative solution. Let's find it using the timeless velocity formula. We're considering positions C and B. We'll examine the motion from position C to B. I set t to 0 at position C. We don't know what t is at B. Let's move on to the next position. I'm setting the position at C to 0 again. This time, I'm choosing the downward side as the positive side. At the position B, s equals h. We found that before, 31.5 meter. The velocities: initial velocity is 0. Final velocity is vb. The acceleration is the same. But there's a difference here. We've changed the positive side. We've chosen the downward direction as positive. Therefore, instead of a equals minus g, it's now a equals g. So, we'll solve accordingly. Let's consider the timeless velocity formula again. Let's substitute the known values here. Let's find vb from here. We can find it. Now, when we substitute the known values, we obtain the relation vb equals square root 2gh. This relation is a familiar and frequently used relation. What does this relation tell us? It gives the velocity at which an object released from any height h hits the ground. In this problem, the height h is 31.5 meter. G is 9.81. If we substitute, we find vb. We obtain 24.8 meters per second. It goes without saying that this velocity is downward. We'll write it down next to it. Now, it wasn't asked in the problem, but I still want to find it. Change in position, distance traveled, average speed. We said this motion is a motion that changes direction. Therefore, the change in position isn't equal to the distance traveled. So, what is it? What is the change in position? Position A is the initial position. Position B is the final position. The difference is 50 meter. As shown in the figure, the distance traveled is the sum of the distance from A to C and the distance from C to B. In other words, it is found by adding the distance h twice to 50 meter. Therefore, the distance traveled is 113 meter. The average speed is found by dividing the distance traveled by the time elapsed. The distance traveled is 113 meter. The time elapsed is 6.6 seconds. If we divide 113 by 6.6, we get 17.1 meters per second. The average speed is 17.1 meters per second. Now let's do a graphical solution. Let's solve this problem graphically. First, let's find the distance h. To find the distance h, I'll draw the s-graph. We learned that the area under the s-graph gives the difference v2 squared minus v1 squared, divided by 2 over the considered position range. Now let's draw the s-graph. We know that the acceleration is constant. Therefore the acceleration doesn't change as the position changes. It remains constant. We also see that the acceleration is negative. If we choose the upper side as positive, the acceleration is equal to minus g. The graph looks like this. It's a horizontal line passing through the minus g position below the s-axis. The area under this graph gives v2 squared minus v1 squared, divided by 2. This area is equal to this value. Let's write the area. Let's set it equal to this value. v2 is 0. v1, the velocity at the initial position, is 40. 0 minus 40 squared, divided by 2 is equal to the area. The area is the base times the height. I write it as minus g times 50 plus h. From here, we can solve for h equals 31.5 meter. We get the same result. Let's move on to finding other quantities. Let's find the time it takes to reach position B and the velocity at which it hits point B. To do this, we'll draw the VT graph. The VT graph is rectilinear. It's a line with a negative slope because the acceleration is constant. We know that the slope of the tangent to the VT graph is equal to the acceleration. It gives the acceleration. If the acceleration is constant, the slope of the tangent to this graph, in other words, its slope, is constant. It's a line with a constant slope. Its slope is minus g. We can find the slope of a line with the relationship delta y divided by delta x. Since we have the VT graph here, we find it with delta v divided by delta t. We're considering points A and C. I'm considering points A and C as the intervals. The final position is position C. The initial position is position A. I subtract the initial velocity from the final velocity. I find delta v. By subtracting TA from the final position, TC, and choosing it as 0, I find delta t. We already know the slope is minus g. If we do the necessary calculations, we find tc equals 4.1 second. It reaches position C in 4.1 second. In other words, the position it returns to, the point marked tc on the graph, is 4.1 second. Now I'll write the slope of this line between points C and B. In the equation delta V over delta t, the final position is position B, and the initial position is position C. At the final position, the velocity is equal to Vb. At the initial position, the velocity is equal to 0. At the final position, the time is Tb. And Tc at position C, Vb minus Vc, divided by Tb minus Tc, is equal to minus g. In this equation, Vb and Tb are unknowns. There are two unknowns. Therefore we can't find anything from this equation. But this equation is the first equation. This is the first equation we'll use to find V and T. We need one more equation. Let's write it using the area under the curve. We know that the area under the velocity time graph gives the difference in positions, or delta s, during the time interval under consideration. Now, the interval we're considering is between C and B. We'll find the area under the curve between C and B. When we examine the graph, we see that this area is a negative area. It's an area below the t-axis. Therefore, it's negative. The change in position from C to B is equal to h. But delta s is minus h. Because we chose the upside as positive, the change in position is negative. It is minus h. This minus h is equal to the area of the triangle. We find the area of the triangle using the equation base times height divided by 2. The base is Tb minus Tc. The height is equal to Vb. Vb times Tb minus Tc divided by 2. This is the second equation. We have two equations for two unknowns. Now we can find both unknowns by solving these two equations together. From the joint solution of these two equations, we find the velocity and elapsed time. We get the same result. Vb equals 24.8 meters per second, downward. T equals 6.6 second. That is, the time it takes to reach position B. Goodbye.